So I'm going to welcome everybody for the afternoon talks. So the first talk is by David de Laat, and he's going to talk about three-point bounds for sphere packing and semi-definite programming. And David, the floor is yours.
Yeah, thank you. So this is based on joint works with Henry Cohn, Andrew Salmon, and Nanda Leijenhorst. So let me, or maybe before I start, let me say, if you have any questions during the talk, feel free to interrupt. So probably I don't see the chat, but maybe Juan can notify me if someone puts something in the chat. But yes, so feel free to ask any questions also during the talk. So here are the topics I want to talk about. So I want to start speaking about the sphere packing problem. Then I want to talk about two three-point bounds, one for the lattice sphere packing problem and one for the sphere packing problem. So I'll explain what that means. And then at the end of the talks, I want to talk about semi-definite programming. So most of this talk will be about discrete geometry and bounds in discrete geometry. And we often solve these bounds using semi-definite programming techniques. And so with Nanda Leijenhorst, we have a project to build a solver for solving these semi-definite programs quicker. So I'll talk about that at the end. So let me start by saying something about sphere packing. So here's the definition. So the ball of radius r in r to the n, and we denote this by brn. And with this, we can define what is the sphere packing, the optimal sphere packing density in Euclidean space. So this maybe looks a bit complicated, but what this is really doing is we talk about density in a non-compact space. So the way we can do that is, so we take a sphere packing, we take a really big ball of radius capital R, and we look at the density of the sphere packing in this really large ball. And then we let the limit of this ball go to infinity. And this gives us the density in Euclidean space. Now, it's a little bit technical that we take the lim sup, because you can define sphere packings for which the limit would not be defined. So we take the lim sup, and then we optimize over all sets of points with distance at least 1 between any pair of points, which corresponds to sphere packing by balls of radius a half. If you don't like the lim sup, you can also just take the limit and restrict to sets P where the limit is defined. You will get the same number. And in fact, basically any definition you can come up with, you can define this in many ways, they will all give the exact same number. So it's really for each dimension, we have one number attached to it, which is the sphere packing density. And then we can also consider an easier problem where we restrict to lattice packing. So packings where the spheres are centered at the points in a lattice. And in that case, we're optimizing over sets P with minimal vector length 1, which again corresponds to packing spheres of radius a half. And of course, the size of the spheres doesn't matter, right? If you have a sphere packing and you scale it up or scale it down, the density stays exactly the same. So this is the definition. So maybe a little bit about the sphere packing problem. So we know the optimal sphere packing in dimension 1, 2, 3, 8, and 24. And the three-dimensional version, of course, is the most well-known version. This is the Kepler conjecture, which was solved by Hales in 1998. And I think this is still one of the most well-known computer-assisted proofs in mathematics. Yeah, and the lattice version is much easier, was solved also much earlier by Gauss in 1831. And then dimension 8 and 24, they're the optimal configurations are the E8 root lattice and the Leech lattice. And this was solved using much simpler techniques than the techniques Hales used, a much simpler method. By Marina Vyazovska and others for the 24-dimensional case, using the Cohn-Elkis linear programming bound and quasi-modular form. So I'll explain more about this linear programming bound. So maybe this is an optimization conference, right? So maybe I should explain a little bit. So because this is a discrete geometry problem, so why should we study this problem? What's interesting here? So I guess, well, the first reason is a really fundamental geometric problem, right? So I'll say, yeah, maybe I'll say more about it later. So the second reason is that, so in the high dimensions, we don't expect optimal packings to be ordered. So probably they are disordered, although we don't have a proof for this or anything like a proof. But somehow the expectation is that in high dimensions, the packings are disordered. Sort of one really vague argument for this is that in high dimensions, volume scales exponentially, but for instance, the number of parameters in a lattice only scales quadratically. So that's but that's not even close to a proof, of course. But if that's the case, that in high dimensions sphere packings are disordered, that makes it sort of even more interesting that in low dimensions they are ordered. So we want to understand exactly when and why optimal configurations are ordered. And we also want to know asymptotically what is the sphere packing density as we let the dimension go to infinity. Yeah, and so the optimal configuration, so the sphere packing problem itself, it's a very simple definition, right? It's a very simple to state problem. But somehow the optimal solutions are very intricate and very interesting. So for example, the Leech lattice, which is optimal in 24 dimensions, has connections to many other areas in mathematics. Yeah, this is, personally, I find this very interesting. And that's also, to me, again, explains why, you could say, okay, that's a fundamental geometric problem. Why does that make it interesting? I think this is one of the reasons that is interesting. So because it is a fundamental problem in geometry, we also get these new connections. So for instance, there are now connections between bounds for the sphere packing problem and problems in analytic number theory, and also the conformal bootstrap program in physics. So I'll say a little bit more about that, but not much. And yeah, this is, I guess, for me, the most important reason. It's a possibility to use a lot of interesting mathematics, right? And then maybe the final reason here is the optimization problems in this discrete geometry often are very difficult. So we can somehow use this to push optimization techniques. We really need to improve optimization techniques for these problems. Okay, so let me say a bit more about the linear programming bound. So here's just this is the normalization of the Fourier transform I want to use. And then we can write down the Kohnelke's linear programming bound. So here we optimize over functions. So functions from Rn to R. And in this case, we take them continuous and integrable. You can play a bit with this function space, but we could, for instance, take them continuous and integrable. And then we have constraints. So we have a normalization constraint. The integral of the function is 1. The Fourier transform is non-negative. In other words, this function is positive definite in some sense. And the function is non-positive outside of a ball of radius 1. And then we optimize the volume of a ball of radius 1/2 times f evaluated at 0. And this is an example of an infinite dimensional optimization problem that actually connects really well to the talk this morning. So this is a linear programming bound, but not with the non-negative orthant cone, but with the cone of non-negative functions, right? Yeah, and then the optimal value of this linear program gives an upper bound on the optimal sphere packing density. So let me say a little bit about the proof, because it's actually very simple. And especially for the case where we take Schwarz functions, so those are smooth functions going to 0 very quickly, where also all the derivatives go to 0 very quickly. So that's especially a nice class of functions to use. So if you take Schwarz functions and we want to prove that it gives an upper bound on the optimal lattice sphere packing density, then we can do that in one line using Poisson summation. So here's the proof. So take for f a feasible Schwarz function, and for lambda a lattice. Oops, this too should be a 1. So a lambda a lattice with minimal vector length 1. Then we want to show that this is the objective function in the linear program. So we want to show that this objective function is at least the density given by this lattice, right? The density you get by putting spheres of radius a half on the lattice points. So how can you do that? So I will go back and forth a bit between this slide and the previous one. So this first inequality, we are going to use that since if x is a non-zero vector in this lattice, then its norm is at least 1. And here we have this constraint that f is non-positive when the norm is at least 1. So that gives us this first inequality here. Then this equality, this is why we take Schwarz functions. So this is Poisson summation, which we can do for a Schwarz function. So instead of summing a function over a lattice, what we can do instead is sum its Fourier transform over the dual lattice. But then we have this scalar here, 1 over the determinant of the lattice. So this is the volume of a fundamental domain of the lattice. And then we get another inequality here. So let's go to the previous slide again. So here we're going to use that the Fourier transform is non-negative everywhere. So we get this inequality. So all of these terms are non-negative for x non 0. So we get this. And now f hat of 1 is 1. So we get this. But if you think about this, this is the volume of a sphere of radius a half divided by the volume of a fundamental region of the lattice. And that's exactly how you have one sphere. If you look at the lattice sphere packing, you have exactly one sphere per fundamental region. So this is the density of the sphere packing corresponding to this lattice. So this is the proof. Yeah, and it's very easy to extend this argument to periodic packing. So periodic packing is given by a finite union of shifted lattices. So that's not difficult to extend this argument. But that's actually enough because the optimal sphere packing can be approximated arbitrarily well by the density of periodic packings. So this proves then that the Cohn-Elkins linear programming bound is this infinite dimensional linear program gives an upper bound on the sphere packing density. Yeah, so this bound is sharp for in 1 dimension, conjecturally in 2 dimensions. We don't know, there's no proof, but it's extremely likely that this is true. There's a lot of numerical evidence. And we now have a proof in 8 and 24 dimensions. So we can numerically optimize this bound by parameterizing functions like this. So by a polynomial times a Gaussian. So this ensures that this is a Schwarz function, or that it's continuous and integrable. And you can then optimize over polynomials P. But due to the non-compactness of this problem, this can never give a sharp bound because, well, actually, Philippe will say more about that on Friday in his talk. But these functions need to have infinitely many roots. So the optimize is due to complementary slackness. So this can never really optimize the bound fully, but we can come arbitrarily close numerically. Yeah, then in a breakthrough result in 2016, Marina Vyazovska, she uses quasi-modular forms to construct the optimal function in dimension 8. This is really a beautiful construction, and she used the numerical data quite a bit to get that construction. Yeah, this proves the E8 root lattice is optimal in dimension 8. And then Cohn, Kumar, Miller, Radchenko, and Vyazovska, they also adapted this to the 24-dimensional case. So I won't give the construction here. It's very nice, but I skipped it here. Okay, so I want to say a little bit about asymptotic bounds. So what happens as the dimension goes to infinity? So to get it's actually very easy to get an asymptotic lower bound. So we can consider a sphere packing for which there's no space to add another sphere, right? And then we can double the radii of all the spheres. But because there was no space to put another sphere in there, this must mean that if you double the radii, that we cover all of Euclidean space. But doubling the radius multiplies the volume by 2 to the power the dimension. So this proves that the original sphere packing must have had dimension at least 2 to the minus n. So we have this bound. So the sphere packing density in n-dimensional Euclidean space is at least 2 to the minus n. And this is actually up to sub-exponential factors still the best known asymptotic lower bound we have. Yeah, the best known asymptotic upper bound is the Kapuscinski-Levenshtein bound. So this is, if you compare this is really far away, right? This is exponentially far away from the best known lower bound. So this is the best known upper bound we have. And the original derivation uses the de Laat-Ketel-Seidel linear programming bound and the geometric argument. But actually, Kohn and Zhao, they show that we can recover the Kapuscinski-Levenshtein bound using feasible solutions to the Kohn-Elkies linear programming bound. So there's really a sequence of feasible solutions. Each dimension you get a feasible solution. And this gives you, which have these objective values. But then, of course, there's a natural question. So is it possible to use the linear programming bound to get a better asymptotic bound, right? So in this project, we did some computations for high dimensions. So here we go, the dimension goes up to 2000 roughly. And on the vertical axis, this is the exponent. So it's the 2 logarithm of the density divided by the dimension. This corresponds to this exponent here, right? So here the dots are the best known sphere packings. The black line is the linear programming bound we computed, and the red line is the Kapuscinski-Levenshtein bound. And then we did some careful extrapolation. And if you do that extrapolation, then you get these 2 lines here. So I don't know how well you can see it, but they're slightly different. So that's actually a conjecture we have. So we conjecture that the Kohn-Elkies bound can be used to prove a better asymptotic bound. Of course, we don't have a proof. This is just numerics. Yeah, just for fun, I also want to show you this conjecture. So we actually have a guess for the optimal lambda. You can prove the optimal exponent. You can prove using the Kohn-Elkies bound. So this guess looks a little bit crazy, right? Because here we only show 3 decimal digits. We actually have sort of 4 decimal digits that we sort of believe. Again, it's just numerical data, but we sort of think we know 4 decimal digits of this number. But then the symbolic complexity of this expression, of course, is way too high to make this guess, right? Based on just 4 decimal digits. But there's actually these connections to other topics coming, such as the conformal bootstrap program, but also a problem related to uncertainty principles. And if you phrase it in that language, then the conjecture is actually that we get 1 over pi. And we sort of thought this symbolic complexity of 1 over pi is low enough that with 4 decimal digits we can make this conjecture. It's still very speculative, I would say. Yeah, so if anyone wants to try, that's, I think, that would be really nice. So there's this Kapuscinski-Levenshtein construction. Yeah, is it possible to give some other construction that does all feasible solutions to the Kohn-Elkies bound that gives a better asymptotic bound? So that would be very nice, I think. Okay, so here are some computations in low dimensions. So this is this column gives the Kohn-Elkies linear programming bound, and actually the only improvement on it known until now is in a paper with Oliveira and Valentin, where we give these small improvements. So now our goal in this project was to give bigger improvements. And I actually first want to go to this easier problem of the lattice sphere packing bound. Yeah, maybe I should ask, because I go to Newton. Are there any questions until now? Okay, so if not, then I continue with the lattice 3-point bound. Okay, so I want to briefly go back to finite graphs. So let G be just a finite graph, a vertex set V and edge set E. And then an independent set is a subset of the vertices, no two of which are adjacent, right? So there are no edges between any of the vertices in the subset. And then the independence number, alpha of G, is the size of a largest independent set. So this is a difficult number to compute. This is NP hard to compute this number. But the Lovász theta number, theta of G, gives an upper bound on this independence number, and it can be computed as the optimal value of a semi-definite program. So I wrote it here. So you have the matrix X, whose rows and columns are indexed by the vertex set and positive semi-definite. And for normalization condition, trace of the matrix is 1, and we have these conditions, so some of the entries need to be 0. And then we maximize the trace inner product of the all one matrix with our optimization variable. So this is, as I said, this is an upper bound on the independence number. And again, it's a one-line proof, similar to the Konelky's bound. So if S is an independent set, then we can construct a feasible solution like this. So 1 sub S is the characteristic factor of this set. And you can check that this is actually feasible and has objective the cardinality of S. And then you can actually, if you look at this construction, the entries of this matrix X actually are all non-negative. So you could add that to this optimization problem, those constraints, and then you get the theta prime number. I think this is by Schrijver, this modification. Okay, so the theta number is multiplicative for the strong product of graphs. And I didn't really write down the definition of the strong product, but I think the easiest way of thinking about that is if you think of as the vertices of the graph as symbols that we want to send over a communication channel. And then think of the edges in the graph as indicating that two symbols can be easily confused with each other. So then basically you don't want to use all those symbols. You want to select the largest possible independent set and only use symbols from that independent set, because then there's no possibility of confusion arising, right? So now what you could do is, instead of sending one symbol at a time, you could send two symbols at a time. So, and then we're going to use this strong product. So the vertex set in the strong product is the Cartesian product of the respective vertex sets. And we're going to put an edge in this strong product whenever a pair of two symbols can be confused with another pair of two symbols. So in other words, we're going to put an edge if the respective first symbols are the same and the respective second symbols are connected by an edge, or the respective first symbols are connected by an edge and the respective second symbols are the same, or the first symbols of the two words are connected by an edge, what do I want to say? And the two symbols in the second symbols are connected by an edge. Maybe I should have written down the definition, but okay, I think this intuition is the clearest way of thinking about it. And what is really, really cool is that if you send one symbol at a time, then you can use an independent set. So if you send two symbols at a time, you can use an independent set in the strong product. But actually the size of the independent set in the strong product can be strictly larger than the product of the sizes of the independent sets in the graph. So sending two symbols at a time can be better from an information theory standpoint than sending one symbol at a time. So that's a really cool, really interesting fact, I think. And then the Shannon capacity of a graph gives you sort of the limiting amount of information you can send if you keep taking strong products. And the fact that this theta number is multiplicative for the strong product implies that you can use the theta number not just as an upper bound on the independence number, but also as an upper bound on the Shannon capacity. And that's actually the original paper where Lovász introduced this this number that was called actually on the Shannon capacity of a graph. So that was really the point originally of introducing this parameter. Okay, that may be a bit of a tangent, but it's just very interesting, I think. So we show, the theta prime number is not multiplicative for the strong product, but what we show that it's actually multiplicative for the conormal product. So this conormal product is not an often used product in graph theory. But what you do here, you again take the Cartesian product of the vertex sets, and now you put an edge if there's an edge between the respective first vertices, or there's an edge between the respective second vertices. Yeah, and then the question is, why is this useful for us? What does this have to do with sphere packing? So, but we can think of the linear programming bound for sphere packing, of the Konoki's bound, as the dual of the theta prime number for some infinite graph. And this means that the square root of theta prime of the conormal product of that graph of itself is actually sort of a new way of writing down the same bound, the Konoki's linear programming bound. So I won't go into details here, but I just want to show you the resulting bound. So we call this delta prod. And this is the infimum of this objective function. So now we have functions on R to the 2n, and we have these constraints. So constraint 2 and 3 correspond to the non-axis in the graph. So we get, okay, you get these constraints here. Yeah, and then it's a theorem that the square root of this parameter is actually this. So the delta 2 is the Konoki's linear programming bound. So there's a theorem that this is actually the same. Yeah, maybe I want to show some computation. So, so as I said, it's a conjecture that the Konoki's bound is sharp in 2 dimensions. This seems to be a very difficult problem. I know that several people have spent quite a bit of time trying to prove that, and just now, yeah, didn't succeed yet. So since this delta prod is sort of a different formulation, it's a different formulation for the same bound, but really different in quite a non-obvious way. So it's not clear what is the transformation from this onto the other one on the primal side. We could hope that maybe it's easier to write down the optimal function here. So we did some computations, and what you see here, this red line is the zero set of the function. So we can write this function f. Yeah, maybe I didn't say that. So we can do some symmetrization, and this becomes just a function of two variables. The orthogonal group is acting on this optimization problem, and if you then mod out the orthogonal group, this just becomes a function of 2 variables. And then it has to be non-positive in this region here, right? So this red line is the sign change region. And then you could try to guess, as the degree goes to infinity, what do you get, right? So here the degree goes up. So this all looks sort of okay. But then degree 15, suddenly this happens. So this is still understandable why this is a feasible solution, but it's not clear why this happens. And on degree 16, we get this. And degree 17, we're back to this normal thing. So basically, the only thing I want to say here is that we have no idea what happens as the degree goes to infinity. Right? We cannot extrapolate based on this. So I think that's quite interesting. That something interesting is going on here. Yeah, and here it's also 0 at these 4 dots. That has to do with this complementary slackness idea. Okay. So, but now we can take this formulation, and in the Konoki's bound, it's not clear how you can strengthen it. But this alternative formulation of the Konoki's bound, it's quite clear how we can add constraints, how we can change it to get a strengthening for lattice packings. And that is because if a lattice is a group, so if x and y are in the lattice, then x plus y and x minus y are also in the lattice. And then we can, yeah, as Etienne said this morning, weak duality proofs are also always easy. So we can do a weak duality proof to show that this is an upper bound on the lattice sphere packing density, but not on the sphere packing density. Or at least we cannot prove that's an upper bound on the sphere packing density. Yeah, so we have theorem, it's an upper bound on the optimal lattice sphere packing density, and also it is at least as good as the Konoki's bound. Yeah, and then we can play with this actually. So we can replace this as let, for instance, by this set, where we also take x plus minus 2y. You can even extend this to all integers. And what's, I think, kind of interesting, if you do that for all integers, you get a problem that has, again, a symmetry group acting on it, a new one, namely GL2 of z. But so, and you would think, okay, then we're very happy with another symmetry. You can sort of mod out that symmetry and get a simpler problem again. But there's really a problem because, yeah, I didn't explain that carefully, but if you exploit these symmetries, what you always do is, okay, you see my constraints are invariant under some group. So if I take a feasible solution, I can take the average over that group action. And then that's also a feasible solution with the same objective. And then you can say, okay, I might just as well restrict to solutions that are already invariant under the group action. But here you cannot do that because this group actually is non-compact. So you cannot do such an argument. So it's not clear at all, even if you have this formulation with a lot of symmetries, how you can exploit that. Okay, so we did computations, and then we get these numbers. So this is just an upper bound on the lattice sphere packing problem, not on the sphere packing problem. But the numbers are interesting, so they're really good, especially in dimension 4. This suggests that this is, of course, just for some degree we could do computations. As the degree goes up, the bounds get better. And it seems like in dimension 4, this could be a sharp bound, right? A lot of the digits are already correct. So the lattice sphere packing problem has already been solved in dimensions up to and including 8. In particular, in dimension 4, it's the D4 root lattice, which was already known for a long time. But since the numerics suggest that this lattice bound is sharp, the question then becomes, can we somehow use this bound in combination with quasi-modular forms to give an optimality certificate? But probably this is a very difficult question, but I think that will be very interesting to try that. Okay, so now I want to go to 3-point bounds for sphere packing. So maybe I start by just giving the bound and then I explain a little bit about it. So let me just write down the bound first. So we fix some constant capital R.
Maybe I have a question.
Oh, yes. Yeah.
So in the previous table, the lower bounds, are they all lattices?
No, the lattice, the lower bounds are on all sphere packings.
On the sphere packings, okay.
Yeah, but up to dimension, including, no, up to dimension 8, the optimal packing is a lattice packing, conjecture. Okay. It's conjectured to be a lattice packing. So for dimension 3 through 8, it's the same.
Okay. So therefore, you I mean, like so this the result suggests that for dimension 9, that should be a lattice much better than the current.
Well, the lattice bound is actually only slightly better than the density is only slightly better than what is written here. So our lattice bound here is really far away from so it's slightly worse. Sorry, I should say.
Okay, slightly worse. Yeah. Okay.
But yeah, what we really would like, of course, but it's not. We would, if we could make the degree really large. We don't know, right? We have absolutely no idea where this number is going. What will be super interesting if it would dive under this number and stay above, of course, the lattice number, right? Because right now, we strictly speaking, we don't know whether this is an upper bound on just lattices or all spheres. We can only prove it's an upper bound on lattices.
Okay.
But we don't actually have an example where it gives a bound that is better than the sphere packing density.
I see. Okay.
But it seems that in high dimensions, the degree of the polynomials we use in the computation needs to be really high.
Okay.
Okay, yeah. More questions? Oh, by the way, this dimension 8, this is a bit stupid. Here we round up to get like really upper bounds. But of course, these numbers are the same, right? So that's just due to and that's why also we leave them out here, because the 2-point bounds are already sharp in dimension 8. Okay, so for 3-point bounds, we fix a capital R greater than 1. And then we write this bound. So now instead of one function, we have two functions. We have f2 in n variables and f3 in two n variables. So for f2, we have the same constraints as for Konalkis. We have the normalization, non-activity of Fourier transform. But f3 is positive definite as a kernel. So think of a really large matrix where the rows and columns are indexed by Euclidean space. And this matrix has to be positive semidefinite. And there's really no relation to the Fourier transform of f3. So saying that this is positive definite as a kernel is incomparable to saying that the Fourier transform of f3 is non-negative. And then we have a bunch of linear constraints again. And then, okay, we proved that this is an upper bound and also that's at least as good as delta 2. Well, that's actually trivial because if you set f3 equal to 0, you get the 2-point bound. Yeah, so here are the numbers. So then in low domains it's not as good as the lattice bound, but they improve a bit more than the previous improvement. That's basically what I can say, right? And also in high domains, they actually become better than the bound we have for lattices, funnily enough. So even though they're, of course, proving something much stronger. Okay, so how do we get...
Can you show the bounds again, please?
Yeah, here it is.
The program.
Oh, okay, sorry. Yeah, here it is. Now, you might recognize it a bit. That comes in the next slide. This is related to k-point bounds.
Thank you.
Yeah, so this is... so where do we get these bounds? So this sort of started with Schijver, who gave a 3-point bound for binary code. So this here the goal was that you could compute the Delft bound, which is actually equal to the lowest theta number or the theta prime number for the binary codes. And Schijver gave a 3-point bound to improve on that. And then Bashok and Valentin, they gave a 3-point bound for spherical codes. And Cohn and Wu for projective space. And then with Machado, who you just heard, Oliveira and Valentin, we gave a generalization to k-point bounds for general compact graphs. And this delta 3, it is a variation on a non-compact adaptation of this 3-point bound for compact graphs. That's one way of thinking about it. There's one tricky thing, and that's the only thing I want to mention now about it. This capital R, this parameter capital R, this is a bit a tricky thing. So why do we need it? So it's not difficult at all to see that the bound actually becomes better as this capital R increases. So then the immediate question to ask is why not just use infinity or some very large number or whatever for this capital R. And that's the tricky thing about this bound. So of course we want to do actual computations. We want to get actual numbers out of this. And for that the only thing we know we can do is parameterize the functions by polynomials times a Gaussian and then use sum of squares techniques. But we have the following lemma. So if f2, f3 is feasible for the 3-point bound with capital R equal to infinity, and f3 is a polynomial times a Gaussian, which you can, if it is positive definite as a kernel, you can always write it like this, as a finite sum over polynomials of this form. But then it's not too difficult to prove that this function actually needs to be identically 0. So, and that's also, I think we were not the first to try 3-point bounds, but that's, I think, what went wrong for what can easily go wrong. It also went wrong and we tried a lot. This took a lot of time to actually come up with this formulation. Because this capital R, you really need it to be able to do computations and to get anything better than the 2-point bound. So this is really the thing that makes it work. And it could be that there's some other really clever way of parameterizing these functions where you don't need this capital R, but we don't know. It's just the only thing we know, multiplying polynomials and Gaussians. That's the only approach we have here. Okay, so this is everything I wanted to say about three-point bounds in a non-compact setting. So are there more questions? Okay, so now I want to go to semi-definite programming a bit more. So this is a project that's almost finished with Nando Leyenhorst. And I want to go a little bit into, okay, so in discrete geometry, we have many bounds on many different problems, but they all sort of share common features. So I want to list them here. So the first feature is that often we have polynomial inequality constraints in few variables. So this is quite different from combinatorial applications, where you very quickly have a lot of variables, but we have only a few variables, say 1, 3, 6, something like that. But we don't just have polynomial inequality constraints, we also have additional positive semi-definite matrix variables in the optimization problem, separate from these polynomial inequality constraints. Of course, if you're going to use SOS techniques, you also get PSD variables from 1, but we already had a few positive semi-definite matrix variables in many of these problems. We also require rather high precision solutions, and this sort of means that we need to use second order methods. So there's a lot of I think exciting research, recent research also on first order methods. And so that's why I put a question mark here. So I'm not completely sure. It cannot be done with first order methods. But it seems like if you need sort of these higher precision solutions, you need that second order methods here are the way to go. And also because they come from these geometrical problems where you often have these orthogonal polynomials in the formulation. And that means that we have inherent bad numerical conditioning, and there's no, at least we don't know how to work around that. So then we need high precision floats. You cannot just use machine precision floats. Yeah, and then often there's clustering, but I want to explain this later. And yeah, nowadays most computations in practice are performed using this STPA GMP solver, which is a primal dual interior points solver using high precision floats. So I want to say a little bit, so I mentioned this already, this point 1, and this actually we saw this week already quite a bit, that you can go from polynomial inequality constraints to simple squares and then to semi-definite constraints. So let P be a polynomial whose coefficients depend linearly on variables in the optimization problem. Now then we can replace a constraint of the form P is non-negative whenever G1 through Gm are non-negative by this Putinar expression, right? Where the SI's are sum of squares polynomials. And then, well, one direction is easy, right? So if these SI's are sum of square polynomials, and then for any x that satisfies these inequalities, it is immediate that the right-hand side is non-negative, right? Because S0 of x is the sum of squares. So this is non-negative, and then the GI of x are non-negative, and the SI of x are also non-negative. And then Putinar shows a reverse to this. I'm not going to go into details. There are some details there, of course. I'm going to skip over them here. And then we can write a sum of squares polynomial using a positive semi-definite matrix. So we can always write it in this form. So and also vice versa. If you have something in this form where A is positive semi-definite, then it is a sum of squares polynomial, which you can see by taking the Cholesky factorization of this AI matrix. Yeah, then what you can do, you can express the left-hand side and the right-hand side of this equality here in the same basis, and then just equate coefficients. So these are going to be linear constraints on the entries of the positive semi-definite matrix variables. So these are semi-definite constraints. So then we reduce the problem to a semi-definite program. Yeah, so now there's this idea of, instead of using coefficient matching, you can use sampling. So at each iteration, the primal dual interior point method is gonna so somehow my voice is a bit bad, sorry about that. So the primal dual interior point method is gonna construct a linear system and solve it to get a Newton direction. I'm not going to give details here, but it's so. But for semi-definite programming, so you just have to believe me here because I don't give details. But for semi-definite programming, constructing this system, setting up the system, can actually be more expensive than solving this system. And this is a bit counterintuitive because the size of a linear system is quadratic in the size of the matrix, right? Solving it is almost cubic. If you use fast matrix multiplication, a bit less than cubic, sort of cubic. So you would expect that solving is much more expensive than setting it up. Of course, computing each entry in the system could be more expensive than linear. So setting up the system can be more expensive after all than solving the system. And so what we can now do is, instead of enforcing this this constraint, this equality constraint, by equating in the same basis and equating coefficients, you can also evaluate both sides at a suitable set of points and equate the result. Yeah, as Lovberg and Perillo observed, this actually gives rank 1 constraint matrices. Now, of course, evaluating them at points, you can also think of this as coefficient matching in an appropriate basis in the Lagrange basis, but you don't really need to do that basis transformation if you can just evaluate. So that's sort of another advantage of this approach. Yeah, and then building this linear system, you can actually speed that up if you have rank 1 matrices or low rank matrices. That's something that was already known in the literature. So we want to use, this, but before I do that, I want to go to this example. And so I've talked a lot about 3-point bound, so let's here also take the 3-point bound by the Schoch and Valentine, but now for spherical code, so we're onto the complex version of the 3-point bound. So this looks a little bit complicated, and I don't want to give all the details. So I just want to say here, this is an optimization problem, where the variables are in red. So these A0 to A2D, those are non-negative scalars. And F0 through FD are positive semi-definite matrix variables. So what is this here on the left-hand side? So these things in blue are polynomials. In this case, these are Gegenbauer polynomials, but it's not important for now. And these Y, these are matrices where the entries are polynomials. So this left-hand side here is a polynomial in U, where the coefficients depend linearly on the entries of these matrices here. And here it's similar. So this here, the left-hand side is a polynomial in U, V, and T, where again the entries are linear in the entries of where the coefficients are linear in the entries of the positive semi-definite matrix variables. And then we have these inequality constraints. So we can do this Putinar approach and do sampling and then get a semi-definite program. So what is a little bit tricky here is that these matrices, if you do, I didn't give them, so you have to believe me if I say this, or actually these matrices here, the Y matrices in UVT, if you do coefficient matching in a good basis, then the corresponding constraint matrices will be sparse. And STPA GMP can actually exploit sparsity. So that's really good. But now, because of the SOS side, you want to do sampling. But if you're going to sample this matrix here, it's not going to be sparse. So you lose this sparsity. But then there's sort of different things we can do. So one thing we can do is we can use that this matrix is sort of low rank still. This happens to be a rank 3 matrix. So we can use that. But what turns out to be better in practice, and this is maybe a bit because I don't give a lot of details, this is maybe a little bit vague. But what we can also do in practice, and that works really well, is we introduce free variables. We write the left-hand side here just in terms of free variables, and we add a bunch of other low-rank constraints to link those free variables to positive semidefinite matrix variables. Then in these constraints, we only have low-rank constraints. And also here we get a little bit clustering already in the sense, but again, maybe this is not completely clear. This could be a bit vague, but because I don't give all the details. But here on the right, for this first constraint, we get SOS matrices here when we do this Putner thing. For the second constraint, we also get SOS matrices, but they sort of appear in completely different blocks in the matrix we're going to build in the interior point approach. And that's what we mean by clustering. So by using this free variable trick, this clustering can also be used a little bit more. And we expect and sort of know in some examples already that if you go to more complicated problems in discrete geometry, this clustering will start to play a more important role. So this clustering can become more important. Yeah, so what we do, and this was Nando's master's thesis project first, and he's now a PhD student in Delft, also working on this. Nando wrote a solver, a primal doodle solver, which can use high precision numbers, which can use parallel computations, so you can use multi-core computations, which can exploit low-rank structures, which can exploit clusters, that's what I just mentioned, and which is written in a high-level language Julia and uses ARP for fast matrix multiplication. And this project really started, so this SDPB, I don't think many people know about this. So this is written actually by physicists for this conformal bootstrap program computations. It's super fast, it works very well in practice, but because they are only interested in these problems appearing in this conformal bootstrap problem, it's sort of very limited. So it can, for instance, only use rank 1 structures. It's only really meant for univariate problems. So basically, you can also see this solver as a generalization of SDPB to much more general structures. Yeah, in this project, we also investigate some more mathematical things. So for this 3-point bound and many bounds in discrete geometry, you want to use symmetries. But it wasn't really clear yet how to combine the sampling approach with a symmetry reduction approach. So we investigate this also. We look at some methods to find good bases and good samples, which can be important for the numerics. We do some numerical experiments. I'll say more about that in the next slide. And also, we look at polynomial matrix programs. So instead of just having polynomial inequalities, you can have matrices where the entries are polynomials, and then you can have the condition that this is positive semidefinite. Also say more about that in a second. Yeah, so here's the numerical experiment. So we choose for the experiment the 3-point bound by Bischoff and Valentin because a lot of computations had already been performed here. So it's a really good sort of test case to see whether this approach can help for speedups. So the best bounds using this 3-point bound were computed by Machado and Oliveira, and they used symmetry reduction to go further than previous computations. So they could go up to DS16, which means you use polynomials of degree 32. So we did the computations with our solver for the same, again for DS16, and then our approach is 28 times faster. So here it helps quite a lot already, and then we could go up to DS20. And if you sort of extrapolate, then it would have, if you would have done these computations using STPA GMP, then our approach will be faster by a factor 40. So there you really, I think, start to see that you can really do more computations by using this solver than you could realistically do before. Yeah, and then we also get new kissing number bounds in these dimensions. But sort of the main goal here was to show the speed up. Okay, so I still...
Is this project published already?
No, it should be published, I hope within a week, but so that's the goal at least. So it should be on the archive in a week. And we're also gonna upload the code and also documentation for the solver. Okay, so I want to say maybe one more numerical experiment, because this connects back to sphere packing. So the Konoki's bound can be extended to give upper bounds for binary sphere packing, so using spheres of radius 1 and r, for instance. And actually what is nice is that the resulting bound, you can interpret it as a matrix polynomial program, so it fits really well into this solver, which really works very well with problems coming from these matrix polynomial programs. So now we can perform computations for larger dimensions and smaller values of this radius. So I don't know if this, maybe I'm putting too much, I don't know if people can still pay attention, so maybe I'm saying too much, so let me know if it's not clear. So we can, for instance, do computations in dimension 2. So the idea is that you now look at the optimal sphere packing density. We have two sizes of spheres, and you can construct any packing using these two sizes of spheres. So we did some computations with Frank and Fernando, but we couldn't go to very small radius r. So for instance, dimension 2, there's this geometric bound, Florian's bound, and we didn't know whether this bound could be better than Florian's bound. But now by decreasing r, where the computations get numerically more tricky, we see that we actually can improve on this Florian's bound. Yeah, but then we get the question. So Florian's bound goes to 1 as r goes to 0. But the optimal sphere packing density does not go to 1. So here we did some computations in very high dimension 24. Yeah, so maybe I should explain this plot. So this 1 here, r equal to 1, this is just a useful sphere packing problem. So this dotted line here is the optimal sphere packing density in dimension 24. This other line is this. So if you think about if the radius of the small spheres goes to 0, then the optimal sphere packing density, basically the best thing you can do is just take the best sphere packing density with spheres of radius 1, and then in the remaining space you plug in, so that is 1 minus the density, you plug in another sphere packing density with using tiny spheres, and you do that again in the best way you can. And then the density you get is this sphere packing density plus 1 minus the sphere packing density times the sphere packing density. That's this line here. So the numerics we do now suggest that as r goes to 0, this bound actually goes to the optimal sphere packing density. So that would be kind of interesting, we think, because then you get a new sharp bound from the 2-point bound. Okay, so that's everything I wanted to say. Thank you for your attention.
Okay, thank you, David. So we have a question in the chat. I don't know if you can see it. From Sven.
Perhaps you can use a maximum. I don't know. Okay. But which group? Because the group here is GL2Z. So invertible 2x2 matrices of the integers.
Yeah, I don't know which group.
Okay.
Yeah. Just, there maybe just a compact subgroup would work, but I don't know exactly which group.
Okay. Yeah, that's interesting. Actually, I will have to think about it. We didn't think about that. So that could work. I don't know if that's interesting. Yeah.
But thank you for the presentation. And I'm interested also in using the solver or trying the solver.
Yeah, so we will work very hard in putting it online as soon as possible.
Okay, do we have more questions? I think Victor has one, yeah?
I have one.
Victor, we cannot hear you. I think we just lost.
I think Fabricio was talking, or not?
I couldn't hear him.
I have one question.
Okay, maybe Daniel can go while Victor fixes the problem.
Okay.
Yes.
Yeah, go ahead.
The 3-point bound for three packing is a problem with functions in 2n variables, if understood.
Yeah, so you use, no, it's, I should have said that. We use the symmetry of the orthogonal group, and then it reduces to functions in 3 variables.
Okay, which is the size of x, y, and the distance between them.
Well, yeah, the norms and the dot product. Yeah.
Not the dot product, the difference, the norm of the difference.
Well, you could think of it that way. So, but
okay, it's the same.
Yeah.
And thank you.
Okay, thank you, Fabricio. And now Victor wrote his question in the chat.
Oh. Yeah, that's a good question. So we don't. So in Julia, there's a very active optimization community right now. So there's this jump, and there's also sort of a standardized way of formulating conic programs and optimization problems in general. We don't use it. So what we use is so our interface is sort of built on top of the computer algebra system NEMO, which is also sort of a different sub-community in the Julia community. And one reason we thought that was convenient is that, okay, so if you do the sampling, you deal with polynomials, for instance, the weights in the Putinar thing, but you also work with sampled polynomials, and you don't really want to. So basically, we extended this computer algebra system with a new polynomial type, which aren't really polynomials, which are already sampled. So you can only evaluate them at samples in your set. And this works very nicely together with the weights. It's sort of easier to formulate these bounds in this computer algebra system. And also it was not complete. So because of this sampling thing, it's not immediately clear how to formulate the optimization problem in this more abstract formulation. What is called? I forgot the name of this. Well, you have jump and you have another library for formulating optimization problems. We didn't really see how to fit it in there nicely, but we also didn't try super hard. So maybe we should try more, and then that can be done actually. So we have our own interface based on NEMO, on this. It's a big German grant, I think, for Oscar to build a computer algebra system in Julia.
Okay. So I think for the sake of time, we can have like a next quick question, because I think the next talk is supposed to start soon.
Okay, then,
Frank?
then just a quick question.
Okay.
The sampling you're using, are you using it while you're solving the SDP, or are you doing it somehow iteratively, like adding more constraints between solving the SDPs?
No, so the sampling is really in the pre-processing. So you have a polynomial optimization problem, then you only use the sample. It's not sampling in terms of sampling instead of doing the inequality constraints, right? It's really sampling to enforce the equalities you need for the Putinar representation. So you really do it first, and then you get an SDP, and that you put in the solver.
Okay, good, thank you.